In the last video we used the work energy theorem to connect the potential and kinetic energies of a particle acted on only by the force of Earth's gravity. As a reminder, the work energy theorem says that the work done by the resultant force on a particle equals the change in the particle's kinetic energy. The important point with the work energy theorem is that it's the work done by the resultant force that gives the change in the kinetic energy. So let's revisit the situation of a particle acted on only by the force of gravity. So if gravity is the only force acting, it means that gravity must be the resultant force. So we can apply the work energy theorem, but we will apply it more generally in this situation. We have a particle with an initial velocity of u vertically down, so its initial speed is u. It falls through a distance y, and the speed at the end of that distance is v. Initially, the particle is at height h above this reference level, which could be the ground, but we can choose any reference level that's convenient for whatever problem we are trying to solve. Okay, so now let's apply the work energy theorem. So we want the work done by the resultant force. Well, that's just gravity, so I'll write Wg for the work done by gravity. So we want the force of gravity on the particle when it's in this position. Well, we know that that's mg, so we've seen this before. We multiply the component of the force in the direction of motion by the distance that the particle moves through, which is y. So we multiply mg by y. And that's equal to the change in the kinetic energy of the particle. So we get the kinetic energy at the end of the motion, which is half the mass times the speed squared, minus the initial kinetic energy at the start, which is half the mass times the initial speed squared. So it's always final minus initial kinetic energy. Now, in this line here, I've just replaced y with y minus h plus h. We subtract h from y and we add h back on, so we haven't changed anything. We have effectively added 0 onto y. Next we multiply mg by y minus h, and then we multiply mg by h. So we get two terms here which are potential energies. We will see this more clearly in a second. Actually, in a previous video we saw that mgh, the work done by gravity on a particle as it falls through a distance h, is also known as the potential energy of the particle at height h above the reference level. And that's associated with the particle when it has speed u. So we are going to put this term together with this term here. This is the kinetic energy of the particle when it's at height h. So we're going to put these energies together. These are the energies of the particle when it's at this position. Okay, so I've added a half mu squared to both sides. So we've gotten rid of this term. But now I want to subtract this term from both sides. So we get rid of it on the left hand side. Okay, so if we subtract it from both sides, on the right hand side we have mg minus mg times y minus h. So now you see we have the sum of the kinetic and potential energies of the particle when it's at height h above the reference level. Now what about this quantity here on the right hand side? Well, this quantity is the kinetic energy of the particle when it's here. What about this quantity here? Well, I just took the minus sign in here, and you see that h minus y, what we get is actually the height of the particle above the reference level when it's here. See, it's h from here to here. So if we take h and subtract y, we get this distance here. So mg times that distance is the work done on gravity, work done by gravity on the particle if it falls through this height, or the potential energy of the particle at height h minus y. So that's what this term is. So you can see that these two terms are the sums of the energies of the particle when it's at this position, the sum of its kinetic and potential energies. So if we call this position up here position 1, for this term here we can just write K1 for the kinetic energy of the particle at position 1, and for this term here we can write P1 for the gravitational potential energy of the particle at position 1. And that's going to equal, over here we're going to have K2 plus P2. We could actually refer to the sum of the kinetic and potential energies of a particle as the total energy E of the particle. So the total energy E of the particle at position 1 is equal to the total energy E of the particle at position 2. Now, we've just shown something that's very interesting actually. The total energy of the particle at this position is the same as the total energy of the particle at any other position, because there's nothing special about y. We can make y any value we like. So the total energy of the particle here is the same as the total energy of the particle here, or here, or here, or anywhere in its path, including at the instant just before it strikes the ground. So you see, we have found a quantity that does not change. In other words, it is conserved. Conserved means it is constant. So the total energy of the particle at one point in its path is the same as the total energy at another point in its path. So we've proven the conservation of energy for objects near Earth's surface, where the potential energy is gravitational potential energy. This result actually can be generalized to situations where we are dealing with other types of forces like electrostatic forces and so on. We could talk about the electrostatic potential energy, but that's not what we will do in this course. We are only going to discuss the conservation of energy for objects near Earth's surface. In other words, problems involving gravitational potential energy. A very interesting fact about the conservation of energy that we just derived is that it applies for a particle that isn't moving vertically down. So let's suppose that the speed at this position, at position 1, is in this direction. So now the velocity vector points in such a way that we get not a straight line trajectory, but some parabolic trajectory. We stated without proof in a previous video that the work done by gravity in this situation is also given by mgy. So we only need to get the vertical distance between the particles, between these 2 points, points 1 and 2. So it doesn't matter how the particle goes from here to here, as long as we are just talking about the work done by gravity, and gravity is the only force acting, or the resultant force acting. As I said before, to prove this, we would have to consider the work done over tiny increments of this path and sum all those works from this position to this position here. So it's an integration problem that's beyond this course. So for example, to get the work done by the particle when it's here, as it moves over this tiny short distance here, we would need to take the force on the particle. Well, that's always constant. It's mg pointing vertically down, and get its component in the direction of motion and multiply that component by this distance here. So it's the work done by the force as it moves this tiny increment, and do that repeatedly. So this is an integration problem that we don't need to worry about, so we can just accept this result and trust that the work energy theorem applies in the same way. The work done by gravity is given by this thing here. So we just need the vertical distance between the 2 points. So this is the work done by gravity, and as we've said before, if it's the resultant force or the only force acting, that's the same thing as saying it's the resultant force, then the work done by gravity is the change in the kinetic energy. Now this is a very useful result for the case of projectile motion, because you see, we can solve problems now much more easily than before. We don't have to worry about the directions of these 2 vectors, u and v. The work energy theorem tells us that we only have to be concerned with the speeds, that is the magnitude of these 2 vectors. That's u and v without the arrows. So if we know the speed of the particle at some height h above the reference level, and we know the height of the particle sometime later, and we want to find out what v is, we can very easily use this result to calculate the speed of the particle at any subsequent height. In the next video, we will use conservation of energy to solve a projectile motion problem. Now, let's consider situations where more than one force is acting on the particle. So gravity is acting as before. So when the particle is at position 1, the force of gravity is vertically down. It's constant force, and the particle is at position 2, of course, doesn't same force. But now we have an extra force because the particle is moving down a straight, smooth track. We know that there's going to be a force on the particle due to it being in contact with the track. That force is perpendicular to the surface of contact of the objects. Let's suppose that this force has magnitude n. As a matter of fact, we know from previous videos that the magnitude of this force is the same as the magnitude of the component of mg in a direction perpendicular to the track, because the particle's acceleration perpendicular to the track is 0. Now, the key word here is that the track is smooth. Now this is very important, because if it wasn't smooth, then the track would not only exert a force on the particle in a direction that's normal or perpendicular to the surface of contact, but the track would exert a force on the particle in a direction along the track and opposing the particle's motion. We know that this force is called a friction force. This happens if both surfaces are rough. Particle and track are rough. So the particle gets somewhat dug in to the track, and the track will exert a force on the particle in this direction. Okay, so that force doesn't exist in this situation. We just have these two forces acting. Now these two forces are constant, so that's because the track is straight. If the track was curved, the normal force would change direction. So if we had a curved path like this, or track, so when the particle is here, the normal force will be perpendicular to the motion, but when the particle is here, the normal force is also perpendicular to the surface of contact, or the velocity. But now you see that we have two different normal forces. They point in different directions. The directions are different. The magnitudes could also be different, but for a vector to be constant, for the normal force to be constant, it means its direction and magnitude have to be constant. So when the particle is here, the normal force is the same as it is here. These two vectors point in the same direction, and they have the same magnitude. We actually know that n is got by multiplying mg by the cos of this angle here, and this angle doesn't change. Okay, we explained in a previous video, and also again in this video, that the work done by gravity does not depend on the path or trajectory of the particle. It's just got by multiplying mg, the weight of the particle, by the vertical distance between the particle at these 2 points. That vertical distance, as you can see, is y. But this is the work done by gravity. To apply the work energy theorem, we have to consider the work done by the resultant force. So we have to be careful here. We can't just say, oh, the work done by gravity is the change in the kinetic energy. We have to consider the work done by the resultant force. Only the work done by the resultant force is the change in the kinetic energy. So let's look at the resultant force on this particle. So of course, when you sum these two vectors, you will find that the resultant force vector points along the track, and that makes sense because the direction of the acceleration vector is down the track, because that's the direction in which the particle is speeding up. And by Newton's second law, the direction of the resultant force is the same as the direction of the acceleration vector. The resultant force F is just a positive scalar multiple of the acceleration. So F and A point in the same direction. So we've seen this kind of problem before for particles on inclines. Okay, so we know the work done by the resultant force is given by this here, but can we get it a different way? Can we get it by considering the components of the constituent forces along the incline? Well, to get the magnitude of the resultant vector, resultant force, we have to consider the components of the constituent forces along the incline. So what's the component of mg along the incline? Well, let's suppose that the angle between the incline and the vertical is theta. Theta can be any acute angle. We know that we need to project the tip of mg onto the incline and get the magnitude of the side adjacent to theta in this right angle triangle. So we know that that's mg cos theta. Okay, so this component, the component of mg points in the same direction as vector f. And then we have to add on to that the component of n along the incline, but that component is 0. Because by definition n is perpendicular to the surface of contact. So the work done by the resultant force is actually the work done by this force here. And this is a very simple problem to solve because this force is constant. Mg cos theta always points down the incline and its magnitude is constant. So how do we get the work done by a constant force? Well, we get the component of the force in the direction of motion. Well, that's just the force itself, mg cos theta. Okay, and we just multiply it by the distance that the particle moves through. So we want the distance along the track from point 1 to point 2. So let's show the picture down here. This is point 1 and this is point 2. And let's suppose that the distance that the particle moves through is L. So you can see that the cos of theta is the side adjacent to theta, which is y, the vertical distance between the particles, divided by the L. And from that we can get L. We just swap L and cos theta. So L is just y divided by the cos of theta. So again, the work done by a constant force is very easy to do. It was the first video on the work done by a force. We just multiply the component of the constant force in the direction of motion times the distance through which the particle moves. So again, we can do all this because the track is straight. Things are much more complicated when the track is curved. The fantastic result here is that no matter what theta is, no matter what the angle of this incline is, the cos theta terms cancel out. So we just get mgy, but that's just the work done by gravity. So the work done by the resultant force is just the work done by gravity. So we could actually also write the work done by the resultant force as the work done by the constituent forces that make up the resultant force. The work done by gravity plus the work done by the normal force. But the work done by the normal force is always 0. Okay, so yeah, this is a general result because work is a scalar. We only just have to add these scalar quantities algebraically. We're not adding vectors or anything like that. So the work done by the normal force is 0. Anyway, we get mgy, and that's equal to the change in kinetic energy, half mv squared minus a half mu squared. Now this line here should be familiar because we know that from this line we derived conservation of energy. Remember, we replaced y with y minus h plus h. Okay, we did some rearranging, so I'm just repeating what we did before when we derived conservation of energy. And we saw that the total energy at point 1 is equal to the total energy at point 2. Okay, suppose that the track was not smooth. Suppose that the track is rough. Well, in this case, we have a friction force acting. So when the particle is moving, the maximum friction force is acting. And we denote that by small f. And we know that the maximum friction force has magnitude mu times n, where mu, the coefficient of friction, depends on the surfaces. Well, it depends on how rough they are and the materials that they're made of. Mu goes up as the roughness goes up. And n, the normal force, you can see that as the track gets steeper, n will go down. And if n goes down, the friction force goes down. That makes sense. Now, what's the resultant force going to be in this case? Well, we have to take this resultant force from the previous situation, the situation of a smooth track, and subtract this vector from it, because this vector lies along the same line as our original resultant force vector. So it's going to shorten it. Shorten it by the magnitude of the friction force vector. So the sum of these three forces, the weight force, the normal force, and the friction force vector, is this vector here, pointing in the same direction as before, but with a smaller magnitude. So F is going to equal mg cos theta as it was before, but now we have to subtract this here. Well, actually n is mg sine theta, but we can just leave it as n for now. So what's the work done on the particle by this force? Well, again, this is a constant force. We assume that this is constant. This doesn't change. The maximum friction force acts no matter how fast the particle gets. The limiting friction, or the maximum friction force, always stays the same. Its magnitude is mu n, and it's always pointing up the incline. So the resultant force has constant magnitude as well as direction. So for that situation, to get the work done, we just have to multiply the component of the resultant force in the direction of motion. Well, that's just the resultant force itself, mg cos theta minus mu n, by the distance. And the distance from here to here is L. Now we know from the geometry that L, the distance between points 1 and 2, is the vertical distance between them divided by the cos of theta. So we can see that the work done by the resultant force is mg cos theta times y over cos theta. Well, that's going to give us mg times y, because the cos thetas cancel like before. But now you see we have this extra term, minus mu n times y over the cos of theta. So by the work energy theorem, this quantity here, the work done by the resultant force, is the change in the kinetic energy, a half m v squared minus a half m u squared. Now, ignore this term here for the time being, and just refer back to what we did before. We had mgy equals a half mv squared minus a half mu squared. Well, we brought the minus half mu squared over. We wrote mgy in such a way that we could bring h into this. So this is what we had. We had the total energy at point 1 equals, just by replacing y with y minus h plus h. And we had the kinetic energy at point 2 plus the potential energy at point 2, mg times the height of point 2 above the ground, which is h minus y. But now you see we have this term here. I'll just shift this term over. Now we call this quantity here the total energy at point 1, the sum of the kinetic and potential energies at point 1, and we call this term here the total energy at point 2. But now we have this extra term. So clearly we can see that energy is not conserved. The sum of the kinetic and potential energies is not conserved. E1 is not equal to E2. Actually, we can see here that E1 must be greater than E2, because we have to add this quantity onto E2. This is a positive quantity. We have to add it onto E2 to get the energy at point 1. So because of the friction force, the sum of the kinetic and potential energies decrease as the particle moves down the track. Okay, so what can we conclude? Well, we can see that if we have a force, in this case a friction force F, that has a component in the direction of motion, then conservation of energy does not apply. Okay, so the important point is that we have this force F that's in a direction along the direction of motion, that is along the track. So we cannot apply conservation of energy. This force N is okay because N does not have a component in the direction of motion. See, the problem with a force that does have a component in the direction of motion is that this force does work on the particle. It actually does negative work on this particle. It takes from the energy of motion of this particle. Actually, it doesn't have to take from it. It could add to it. I mean, we could have imagined a force in the same direction as the direction of motion, and a third force, instead of just N and mg, and this would add to the energy of motion, or the kinetic energy of the particle. So we could not apply conservation of energy in that case either. So the key point is that in order to apply the conservation of energy, we must make sure that gravity is the only force which has a component in the direction of motion. See, the component of gravity in the direction of motion is this here. N has no component. Okay, it's worth repeating the condition for applying conservation of energy to a particle's motion. We apply it if gravity is the only force that has a component in the direction of motion of the particle. In the next video we will see some examples. Finally, we will consider the situation of a curved track. Now, we will deal with a smooth track. The track can be curved in any way we like. Now, in this situation, the normal force will change. So, for example, when the particle is here, the normal force is perpendicular to the surface of contact, so it will look like this. So you can see that its direction has changed. In general, its magnitude will change as well. The force that won't change is gravity. That's always vertically down and has magnitude mg. Now, the work done by the resultant force in this case is the work done by gravity, which I will write as wg, plus the work done by the normal force. Okay, so there's only two forces acting, and the only force that has a component in the direction of motion is gravity. So we might expect the work energy theorem to hold here, and hence conservation of energy should also hold if there's no friction. Well, we said before that the work done by gravity in this situation is also mg times the vertical distance through which the particle moves. So we know what that is. It's mgy. We didn't prove that because, as we said, it involves chopping up the track into tiny increments and getting the work done by gravity over each increment. But if you were to do that using an integration technique, you would end up getting mgh. Well, actually it's mgy here. Okay, so we're going from position 1 to position 2. That's a distance of y. Okay, so that's a result that we just take on trust. Okay, we proved it for the case of straight line tracks at any angle theta to the vertical. It's also true for a curved track. It's the work done by gravity. Now, what about the work done by the normal force? Well, here again we would have to use an integration technique. We would have to get the work done by the normal force over each tiny little increment. But that's always going to be zero, because the normal force is perpendicular to the direction of motion. See, we want the component of the normal force in the direction of motion to get the work done by the normal force as the particle moves through a tiny increment. And that component in the direction of motion is zero. We make the increment small enough. And then we imagine summing all those works, and we're going to get zero. Zero for each increment, so if we sum them all, we will get zero. So we can put a zero here for the work done by the normal force. The normal force is constantly changing. So you see, we just get mgy, and we know what the consequences of that are. Okay, the work done by the resultant force is the change in the kinetic energy. So now we're back to the situation that we saw before. So we've seen this twice before. We know what the consequences are. We get the conservation of energy. The total energy at point 1 is equal to the total energy at point 2. So we can apply the conservation of energy to any smooth track.